All right. Can you still see this?
Yep.
Excellent, excellent. Okay, yeah, please feel free to interrupt me at any point in time. It's better to have a discussion than me just reading through. Also, there's always a chance that I'm a bit fast when I talk about this. So this is a paper that is quite old, I think 2002, and it was fairly successful, but it's not like one of these blockbuster paper that everybody has read for sure. Um, what is the paper about? It's mostly about games and how to solve them. Um, in particular, it tries to answer the question, how can we find an optimal strategy to a game? And it tries to dig a little bit into the direction of how much do we have to know about what other players think in order to solve a game, and why is it important? Well, these sort of games, when we say games, it's more like a procedure, actually happen all the time in life, being like actual games, video games, team sports like football, but it could also be some negotiation or auctions. These are all considered games in this context. Um, oh, bloody hell. Let's get a bit into the background. Yeah. What different kinds of games there are based on game theory. One very common one is the Markov decision process. Essentially, it's a mathematical setup where you have a bunch of states, you have a bunch of actions, you are just a single player in this setup, and you have an environment. And whenever you are in a state and you do an action, you end up in a different state with some probability. It can also be deterministic, but either way, your state is not the same as you continue along the steps, and you also get a reward for doing that. And the typical question is, okay, what is the best policy I should follow so I can maximize my future reward? That means that short term I want to get reward, but also long term I want to get some other reward. Now, in order to balance the two, there's typically a discount rate that says how much more do I value current rewards versus future rewards. And in many cases, like a game of chess, which is not one of Markov decision process, but typically in such games, you often care only for the very end whether you win or lose, rather than whether anywhere in the meantime you have some favorable position. The one example is the multi-armed bandit. It's essentially you have several levers you can pull, and you get a different reward out of each. You actually don't know what is a transition function. You don't know what is the reward distribution. How can you best find out which lever to pull in order to maximize your long-term benefit? This has quite a lot of practical applications. For example, in the ad space, if you are a Google or a Facebook and you have a user, you want to show them some ads, you have usually a finite choice to make, or you sample from a finite number of ads, but you can only show them one. And there are some very smart algorithms that try to maximize the expected revenue in terms of click rate, but also then, of course, the amount people pay to put the ad up. That optimizes the reward for Google or Facebook in that instance. Yeah. So and it's a game in the broadest sense that it's only you playing. There's no other player. The environment is sort of static. It might be stochastic, but at the end of the day, it is still not dynamically changing at all. The next set of games is slightly different. It is the matrix game. Here you have n players, and each player has a number of actions available to them. And for each action combination, there's a payoff. And again, it could be stochastic payoff. And this is called a matrix game because for two players, you can always arrange it in a matrix. For more players, you can arrange it in some sort of tensor with a payout for each player. So a two-player game typically has two matrices, one for the first player, one for the second player. And what is the strategy in such a game? A strategy is, for a single player, a distribution over the actions. And of course, the probabilities of those actions have to sum up to 1. That's the only restriction there is. And a total strategy is essentially the strategy of one player and the strategy of all the other players together. So typically we call sigma minus I is the strategy space of all the other players that are not that player. And again, the payoff can be stochastic. However, each player as well has typically a utility in as much as how much they prefer perhaps a low variance scenario over a high variance scenario. So they can still, for each point in the matrix, essentially give a single number rather than a distribution of numbers. And what are some examples? Here we have in R1, that is a game called Matching Pennies. Apparently goes back to a real game where one player puts an odd or even number of pennies in their hand. The other player has to guess are they odd or even, and if they guess right, they get the pennies. Otherwise, they lose the pennies. And there was some newspaper article that apparently one schoolboy was really good at this and essentially took the lunch money of everybody in the school. And that's game, because it's a very simple game, has a very simple matrix, made it into the literature and is often used as a sample. Number 2 is the standard.
Yeah. You didn't find any. You didn't have fisticuffs.
No, they were gone.
They're gone.
Yeah.
I've gone back to bed.
Sorry, was there a question?
Their calls like that. But even their calls. Like, as long as my car, my gas guzzler.
Try to mute them.
I do the gas guzzler, but not.
The second game is rock, paper, scissors, where each player has 3 actions: rock or paper or scissors, and there's always one action can beat another action of the column player. And when they are the same, they are 0 reward. And you notice that in these first 2 games, the payoff function of one player is the negative of the payout function of the other player, meaning that the moment one player wins, the other one loses. The third game, it's a coordination game, is slightly different, where both players benefit from using the same action, but which of the action they choose? Should they both choose the first action or both choose the second action? It depends on the player you ask. So one player would prefer both of them using the first action, the other player would prefer both using the second action. However, the moment they disagree, none of them gets anything. So that makes it a very interesting game to analyze. It's not zero sum, it's called a general sum game. Some definitions that are quite useful in handling these kind of games is the first one is the best response function for a player. That is, if you are a player playing against one or many other players, the moment that they fix their strategies, it doesn't matter what they fix them to, but the moment they fix the strategies, you typically have one best response how to answer. And that obviously depends on what the other players are doing. If you think of rock, paper, scissors, if your opponent chooses rock 40% of the time and the other ones equally, then you actually benefit from using papers all the time, right? Because even though you don't win all the time, you maximize your chance of winning by doing that. Related to that notion of best response is the idea of a Nash equilibrium. That is a strategy or a point in the total strategy space. So your strategy and all the opponent's strategies mixed together in one vector. And the special point here is that each player individually is a best response, behaves in the best response with respect to the strategy of all the other players. So if each player sees the other players as static, they just look at their own strategy, they have no incentive of moving away because they already optimized them. Yet overall, they're also still in an optimal, and no player has incentive to move away, which makes this a dynamically stable point, because one player would have to purposefully do something that goes against their own best interest in order to move away from such a point.
I guess that also means that there's no such thing as all the other players fixing their strategy and there being 2 different optimal strategies for one player.
It depends very much on the game, and that is, I think, one of the big problems of game theory. It turns out that in cooperative games, we go back here, there is actually two sort of best strategy, right? So the moment two people agree to go for the first action, no player has a benefit of moving to another action, even though player two might say, okay, if both of us were moving to the second action, we both of us, I would get two and the other one would one. However, the moment he moves away, he's already in a losing position. So so this is an example of a game where there are actually two stable points in this.
But what I mean is that, say that you fix the strategy of all your opponents.
Yep.
There's only one optimal strategy. Like there's only one can there be multiple optimal strategies when all of your opponents?
Ooh, I would say it should be one, but don't quote me on this.
Yeah. Okay.
It's the funny thing is that the nature of the game can be quite different between zero sum and non-zero sum, and the number of equilibria can easily vary, and I think it can be a continuum even in certain cases. And funny enough, like if you think of something like the prison dilemma, where the rational thing to do is not necessarily the best for everyone, it can become quite counterintuitive as well. There are some special cases which are quite important. One is the purely competitive play. We already talked about when you have two players and one's earnings are another one's loss. So in that particular case, there is always a natural equilibrium. Another case is quite interesting, is the purely collaborative case where every player has the same payoff function, and that typically means that the players somehow have to coordinate their efforts. And yeah,
Arvid, there's a question.
Please.
I'll read it out. Presumably, there's one on the discussion we were talking about before.
Mm-hmm.
Presumably, there's one optimal value, which is some complicated which in some complicated or repeated games may be achieved with multiple strategies.
I don't know. Honestly, if it's a collaborative repeated game, then probably.
Sorry, I was thinking of like the prisoner's dilemma, but repeated over multiple times. But I think this is probably a sideline to the
yeah,
to the main discussion here. Sorry. Yeah.
I don't actually know whether you can solve the prisoner's dilemma. You need to at least work with some sort of boundary conditions, for example, that you don't know how often it is repeated, where the number of repetitions is unknown, right? Because the moment there is a finite repetition, you sort of can say, okay, if it's the last case, I can actually benefit by deviating and so on and so forth. So it's I don't know enough. That's the short answer.
Yeah, fair enough. Thank you.
Sorry, I think it's slightly cut off. Too much to it. Yeah, and generally once you have this matrix given, you can find in zero-sum games the Nash equilibrium by using linear programming. Can become problematic for large matrices, of course. What is a stochastic game? Now that is, we just talked about the Markov decision process, where you just move from state to state and try to optimize some kind of reward. And we talked about matrix games, where you and some other players have each some finite choices and the payout function. And this is when you combine the two, where you have when you play matrix games, but in a state sort of setting where based on your action you move to a slightly different matrix game every time. So again, you have n players and state space. You have the actions, which I don't think have to be the same as you go from state to space. So if you go from state 1 to state 2, you might remove actions or increase the number of actions that are available to you. You have, again, a transition function. And a reward function, again, depends on transition, might be stochastic, and so on and so forth. And of course, each player will try to maximize their own long-term reward, meaning that even though you might win a particular game momentarily, if that pushes you into a state, a set of states where in the long run you make more, return or money or whatever it is, then that might be the wise thing to do. And Shapley, so he got the Nobel Prize, I think, in 2012, showed that there's for zero-sum games there is still equilibrium, and Fink also showed that for general sum games that is also true, but they are not unique anymore. So these generalizations definitely have solutions. Just finding these solutions can be quite tricky. And you can also see that if you take these stochastic games and take some special cases, for example, if you set the number of players to 1, then again it's a single player in a Markov decision process. So the Markov decision process comes as a special case out of stochastic games. At the same time, if you take the state space and reduce it to 1, so you only ever transition from one state to the same state back again, then it's just a standard repeated matrix game, and all of the stuff we prove about matrix games should still be applying here. Sorry, I might be going a bit fast, so please interrupt me if I'm too unclear or if something needs more explanation. In trying to find solution for these stochastic games, there are some desiderata. For one is that if the first one is called rationality, if the other players are doing always the same thing, so they're not moving about, then whatever you do should, at least in the long run, optimize your returns. So any algorithm or family of algorithms that you implement should be rational in that you maximize so the profit you get. And the second one is that if you run something, some algorithm like this, you should be able to converge if the other players also are converging. And these two properties actually are not that easy to fulfill at the same time. You can prove that, of course, if you are rational and you converge, then you are in a Nash equilibrium. And so people tried solving these things. As
If we go back to the other slide,
this one or the one before?
The convergence side.
Yeah.
Converge to policy. So the first one is saying you will converge if all the other policies are stationary, and the second one is saying that no matter what, you'll converge.
The first one states that if the other ones are stationary, you maximize your best. You get to the best response.
Okay.
And the second one is that you do converge to something guaranteed. And we're going to talk about some examples in a moment where you can always show it's one or the other, but it's surprisingly hard to get something that actually does both.
Well, why would you want to converge to, if the target is moving based on the other players, why would you want to converge on a policy that's stationary?
Because many games like rock, paper, scissors, you know that a pure best response doesn't exist, right? So you always have a mixture of policies is your stable fixed point, right? And if your algorithm is incapable of ever learning a mixture, then it's always going to be bouncing around and it's unstable. And plus, of course, as a theorist, you often are quite curious about what is actually that stable point. Is there in this case you have this competitive game, is there actually a fixed point? And if yes, you want to know what it is rather than something that bounces around something and you don't really learn much about the nature of the fixed point.
Okay. Is this also sorry, I'm jumping in there. Is this also kind of saying that if it's possible to converge, like if everything else is behaving in some kind of rational way, then you should converge? Like the idea is.
So yes.
Is that essentially what Property 2 is saying? That if there is a policy to be learned, you should learn it.
Yeah, I think
number one is if there is a policy to be learned, you'd be learning the best version of the policy.
Yeah, I think that the second one is almost like if you have a number of agents and each of them uses this particular algorithm, then you should converge, which I think is a slightly different way of saying it, right? So because rationality means that if one agent moves away from their optimum choices by whatever reason, you want to capitalize on that still. That's the rational aspect of it. But the second one, I think, states that if each of you is playing this particular algorithm, you want to converge to something that is that converges, and of course, because of property 1 is also rational to converge.
Okay, thank you.
So in the past, people tried different things of solving matrix games, stochastic games, And they usually would involve one standard matrix solver from game theory, so usually linear or quadratic programming, and something that does your reinforcement learning stuff, or reinforcement learning process, which is usually some temporal differences. And just by combining different versions, you can actually get quite a large class of different algorithms that more or less should run these should be able to solve stochastic games. However, they often have some drawbacks. I think we're going to discuss them here. So first one is Q-learning. What does it do? You, for each state, you sort of keep a model, which is your Q function, which gives each action a value. And as you play your algorithm out, your algorithm always chooses epsilon greedy. So that means that as you play in an episode or something, you take the best action that you have available based on the Q function you currently have. You observe the rewards, and only every now and then, so maybe 1 in 10 times, you choose your action randomly. Otherwise, you would sort of get stuck too much into the same policy, and then your Q function would not be correct either. And as you do this, you update your Q value with the reward that you are getting in your episode, plus the maximum of the maximum value you can get out of the next state you have transitioned to. And you sort of train it so that your Q function best approximates your reward plus expected future reward. And I think this is very clearly rational, right? So if your opponents don't change their policies, you're going to eventually accrue more value in the function that maximizes your that maximizes your future rewards, and so you do flip over to the best strategy, provided it exists. The problem is that it also chooses what it thinks is the best action 100% of the time. So if it is the case like rock, paper, scissors, it could very well happen that, because the opponent plays randomly, say in the last batch update you had for pure randomness choice a bit more rock than anything else. So suddenly your best action becomes paper, but in the next batch it might be slightly more paper, and so you go from going all into paper, you go all into rocks, and so your algorithm is not stable, right? It again bounces between what it thinks is best option. But we do know already that the best option most stable option is not a pure strategy, but it has to be a mixed strategy, and this Q learning definitely can't do that. Now one of the extensions is minimax Q, where again very similar update rule of your Q function, except that rather than using the Q function itself to establish what is the best action, you take so you assume, okay, you're both in the next state, the payout of that state. If we assume that the other player is completely rational, then this again becomes a standard matrix strategy game, and we can solve it with a Nash solver, and we can sort of assign what is our expected value of the next state, and so we can then try to move into that direction. Now that is guaranteed to converge. The problem here is that we don't have actually any guarantee that the other player is going to play that rational, right? So players sometimes are irrational, and so that means also that our algorithm, our minimax Q algorithm, is not rational. So we don't necessarily choose the action that, based on our learning, optimizes our long-term reward. But it will converge in self-play. It's kind of nice. Also, you need a Nash solver, which I learned from personal experience. It can be quite hard getting a good one, and some free implementations that exist out there, they do break once you make your matrices big enough, which is very annoying.
Can we go back to the value function real quick?
Yeah.
So
So that is supposed to be the Nash, the
Sorry?
the
Yeah.
value you would assign to that game if everybody was to play at a Nash equilibrium.
how do you, is that something you'd have to learn the value function as well? Is that the idea?
But well, it would be yes, sort of. Actually, yeah, you have to learn the value function. So essentially, because your payout function is the reward plus the value of the future states you might move into. So it becomes a value function dependent payout function, which you then solve with natural equilibrium. So you have to solve it essentially for every state all the time. Whenever Q updates, of course, your payout matrix might change, and then you have to resolve it. So that also becomes quite expensive. Yeah.
Okay.
Lastly, one option is opponent modeling, where you keep a track in each state what were the actions chosen by the opponent, and it is rational, right? Because and then optimize essentially for, given I have an inkling that the opponent is going to use this action is more likely than others, what value should I choose? And of course, it is rational to do so. So if the opponent keeps a fixed strategy, you or try to find the best action. However, again, it converges to a pure strategy, so it doesn't really converge to mixed strategies, which is what we know is the right thing to do. So it's also not complete in what we want. So let's look a little bit about the actual problem itself. What is the problem that makes these algorithms when maybe unstable if two agents are playing against each other. Now the toy model that we study here is just a 2-player game with 2 actions each. So the payout matrices are fairly simplistic. They are just each player has essentially 4 numbers in the payout matrix, but they're not necessarily summing up to null either. So this example is a mixture of a competitive game or a collaborative game. Could be anything really. And again, a small r is the actions on payoffs of the row player, and c is of the column player. And of each player has only essentially one parameter to optimize, right? So each player can choose what is their probability of choosing their first action versus the second action. But of course, because they have to sum up to 1, each player's probability distribution is essentially only specified by a single number, which makes this problem quite easy to analyze, because there's a lot less freedom than in bigger games where say rock, paper, and scissors, where you have 4 free parameters in order to describe your strategy space. Yeah. Now each player is say supposed to be playing rationally, and what does it mean? Each player knows their own payout function. They know what is the strategy of the other player, so they can calculate what is their payout function. It's just a matrix dot product, and then what they can do is they can optimize for their parameters, and both players can do that, the row player and the column player. Numbers, both linear combinations have a factor that contains a product of alpha and beta, and these numbers are u and u prime, and we just write them out here just because they become fairly important later on. But the important thing to know is that they only depend on the payout matrices of each player, and they are, for the purposes of one game, static. And now what can happen when a player tries to optimize their payout? Of course, they try to move their alphas or beta, their probability parameters, in the right direction. That makes their algorithm more stable. And if they go on, it looks of course like this. And we say that at the boundaries, because the probabilities can never be bigger than 1 or smaller than 0, they essentially are reflected back into the unit square. Does it make sense so far? I mean, that is just very standard optimization, right?
Yep.
Perfect.
Yeah.
Of course, that is rational, but the question, but it's not always convergent. We're trying to find out why is it not always convergent. And the idea is, of course, this is we can make this a very special version of this algorithm by making the step size of the update very, very, very small, right? So that in each update this really becomes a linear problem. And we essentially get this matrix where we only ever have the alpha and beta, so player 1 strategy and player 2 strategy or probability of their first action interact via these u and u prime, whereas the rest is essentially a static vector, and we get this differential equation, right? So that the way the strategy can change is via this matrix multiplication of this U matrix and the strategy itself plus some constant offset. And if we assume that U is invertible, which is in most cases the case, then we can analyze the dynamics of the system. If it's invertible is, for example, a stable fixed point, the question is, of course, where does a stable fixed point sit? But at this point, we know that if we sit exactly on a fixed point, we are stable. So each player has no incentive to change that strategy ever as time goes on. But we can now analyze what happens if we are not at that fixed point, but rather a very small offset away from that. How does this offset from a stable fixed point changes? And essentially what we do is we take out the standard offset and we get a linear equation just for the deviation from the fixed point. So where the time derivative of the deviation is the matrix product of the deviation itself. So this is a matrix differential equation, vector differential equation. And we can study that. First, one big help is to decompose, and you can pretty much always do it, decompose your deviation into eigenvectors. And what is an eigenvector? Well, an eigenvector of matrix U is a vector that when you apply it, if you apply the matrix to that vector, what you get is a constant and of times that original vector again. And the nice part is the moment you have such a structure, so each eigenvalue also has an eigenvector. If you assume it that the time dependence is like this, so meaning that if you have a time dependence is essentially an exponential in front of a constant vector, so it's a very simple time dependence, if you will. If you plug that into this equation, you can actually show that it indeed solves it, just because the temporal derivative is essentially just your prefactor from your exponential, and that you can reabsorb into the eigenvector, and it just solves it. So that means finding the eigenvectors and eigenvalues can tell you a lot about how this how a small deviation from the equilibrium will behave in the long run. Is that clear? It's a bit fast.
I think so.
Okay. How do we find the eigenvalues for matrix? Well, we just take the minus lambda, the matrix minus lambda, the identity in that space, and take the determinant, and becomes, in this very simple case, a quadratic equation. And the quadratic equation has eigenvalues, which are plus minus the square root of u and u prime. If you remember, u and u prime were only depending on the payoff function of each player, and so they are static for the game, meaning that also the eigenvalues are essentially values that are static within the game, which is what you would hope. And what is quite interesting, it is the nature of the eigenvalues, or if the nature of the product of the u values tell you what is the nature of the eigenvalues. So if u times u prime is positive, then the eigenvalues are a positive and a negative number. If you go back, what does a positive or negative lambda do here? Right? If it's a negative number, you have a small delta and you multiply it by e to the minus delta, some small time step or whatever you take, then your absolute magnitude of delta will become smaller and smaller and smaller. So you essentially fall back to your equilibrium point. So it becomes a stable equilibrium. On the other hand, if lambda becomes larger than is positive, then any small deviation grows and grows and grows until it is sort of blown out of your state space. In this particular case, because we are on some valid probability distribution, we essentially would move to some boundary value. The really interesting bit is what happens when they are negative, and when the product of u and u prime is negative, then we get purely imaginary solutions. We're going to see in a moment how it looks like. Of course, cooperative games where u equals u prime, because they are by definition the same game, always going to have these real eigenvalues where you converge to stable fixed points. But in our case, the one we really most interested in is the zero-sum game. We're always going to have a imaginary eigenvalue, just by the very nature that the payoff functions are opposite of each other. And so we know that for zero-sum games in this space, we're always going to have solutions that are imaginary, and the imaginary solutions actually are always circling around the equilibrium. So we never reach the equilibrium, we just move in circles around it. This is how it looks like. So we can ignore the non-invertible case, but if we have real eigenvalues, either we move towards it or then get pushed out to the sides. So it's always going to be more than one stable equilibrium, right? So in a purely competitive case, but you can choose on which stable fixed point you want to align to, and it sort of depends a little bit on the starting position, whether you end up in the top right corner or in the top left, bottom left corner. Whereas in the zero-sum game, your solution is going to exhibit this rotating behavior, and that is IGA. Sorry, that stands for infinitesimal gradient ascent. So if you make your updates small and small and small enough, you would expect these circles to appear.
Sorry, just translating this back into some of the games earlier. So what we're talking about in real eigenvalued versions, if there's a chance where there's a cooperative game with equal payout, then you'll have convergent solutions that are stable and the same. If you have a chance,
equal payout, right? So even in different payouts, you would still, under IGA rules, converge to one or the other. So say if you are the row player, and say the bottom left equilibrium might have a higher payout for you than the one above. If you move infinitesimally slow steps and you start somewhere up here, or actually anywhere on this side, you are going to end up in the upper right corner, even though that might be
because there's only two actions. It's a two-action game.
Yes.
Right, of course. Yes. Okay, yeah, there we go. Right, cool.
Yeah. Now there is a theorem from another paper that they were actually the ones that first built up this IGA algorithm and analyzed it, and they say, okay, for all intents and purposes, either you are converged to Nash equilibrium, so that would be this case, or your average payoff over time will converge to the expected payoff of a Nash equilibrium. Why is it? Of course, if we have these rotating solutions, you can decompose it into the different components, into a sine and a cosine component in the payout sandwich, and you can show that if for full rotation, the parts that come from the sine and the cosines essentially average out, and so that means that only the value that is coming from your stable equilibrium, from your Nash equilibrium, actually contributes to your average payout matrix, which is why this theorem holds true, which is kind of cool. So that already shows that using these IGA rules, you can already get, at least for this two-player, two-action game, you can get the value of the Nash equilibrium without ever actually reaching it, which is useful, if you will. Sorry, small interlude. I was actually trying it myself on a rock paper scissors game, but rock paper scissors is relatively easy to solve because of the very strong symmetry that rock paper and scissors, they all, you can just relabel them, and so they must have all the same probabilities, so they must be a third, a third, a third. But if you make your payout matrix slightly imbalanced, so here I have that rock has you get a payout of 2 when you play rock and win, then your solutions of the best way player 1 and player 2 can play are not the absolute symmetry point, but rather slightly offset, and it becomes also slightly counterintuitive that your best action doesn't always have to be actually replayed the most often, because your opponent would know that, and you can actually get away often with playing your best action less often. The average utility is roughly the same. And if you put it into one of these algorithms, you see that if we make it eager-like, so we have very small updates, we get this oscillating behavior. Now this is for one player, and you see it's always blue, red, green, blue, red, green. So if I play blue, means I play predominantly paper. What's going to happen is that the opponent is going to see, oh, he's playing a lot of paper, I should use scissors next. And so eventually I'm going to realize that they use a lot of scissors, so I'm going to split over to rock, and then so on and so forth. So I don't get these stable values. Ideally, what I would like is that my algorithm converges somewhere on this blue, green, and red dotted line, but it doesn't. This is how it looks in this ternary space. So we see that it is rotating in weird circles around us, and it gets sort of bounced back at the boundaries. Now we come Wolf. Wolf is actually now the actual part of this particular paper, but they implemented.
Sorry, just before we get away from that, you said that if there's imaginary eigenvalues, then you might end up with an expected payout that is equal to. So on your sine graph that you had there of the shift, or the previous one, right? Yeah. So do you think that, well, it doesn't converge to the equilibrium for rock? Does that sum to the equilibrium?
Yeah. So here
that's the sum.
There's probably first of all a bit of a caveat here that here we very definitely hit the boundaries, right? And the boundaries get rid of this perfect sine.
Okay, yeah, fair. Yeah,
so
okay.
if I start, I think it goes if I'm close enough to the actual equilibrium point and rotate around that so that I don't bump into any boundaries, then that holds true. I don't actually know whether that is also necessarily true for the probabilities, but I think it also means that the probabilities should, on average, be the right value.
Okay, thank you.
Comes up as quite crucial actually later. So what do? They implement Wolf, and Wolf stands here for win or learn fast. So essentially you still use your eager update rules, but now you have these additional factors in there for your row player and your column player, and you still update very, very slowly. However, when you think you are winning, you want to update slower, and when you think you are losing, you want to update faster to catch up. And well, that might be generally good life advice. When they actually try to figure out, does this stabilize the algorithm? One part of it is the question of what does winning mean, and the idea is that, okay, in this particular setting, both players know that there is a net equilibrium, and so they have essentially a reference strategy, and they can at any point in time compare whether their currently implemented strategy is doing better or worse than the reference strategy that they are comparing to. So they don't necessarily have to see, two players don't necessarily have to agree on the same Nash equilibrium. So this goes beyond that, but each player can essentially choose whether they win or lose. And yeah, players then check what is my expected payoff given my current strategy versus my Nash strategy, and if I'm winning, I should be careful. I don't want to update that fast, so I use a minimum value of L. And if I'm losing, I want to update a lot faster, or not a lot faster, but faster. And the other player, of course, is going to be the other way around, objectively. But of course, when they are winning, they still want to update slower than when they're losing. How does it change our dynamics? Well, we just put it back in. We see that the overall structure has not really changed. If we plug it in at any point in time, but each player is either winning or losing, we can see that the eigenvalues, if provided these are constant for a moment, we still see that the overall behavior is determined by this u prime, which is the game parameters essentially. So if we were in a real eigenvalue solution before, we are still in a real eigenvalue solution because LT and LC, or R and LC, they are always positive, right? So this is just a positive prefactor that comes out of here. So we still decide by u and u prime whether we are in a real or complex plane. And there are a couple of proofs that they come up with. So one is if both eager converges, it converges to Nash equilibrium. They sort of say, okay, if my strategies don't move, then there must be a zero gradient where I am right now. And because we also see that the algorithm is rational, that it always tries to maximize their expected payout, this convergence suggests that it is indeed in Nash equilibrium, one of them. And that covers the real eigenvalue. Now, the imaginary eigenvalues, that is actually the case that is interesting, because that is the case where Igor and Wolf-Igor are slightly different. And this case is special because it already means that there's only a single Nash equilibrium there in this space. We know the eigenvalues, and when we know the eigenvalues and eigenvectors, we can actually look at what the solutions are, and we see now they are ellipses. And the interesting bit is that I don't know what they're called, the size of the axes depend on the ratio of LC U over LR U prime, right? So if you can sort of think of it that the ellipses could be elongated in one direction or in the other direction, dependent on what the ratio of LC over LR is at any point in time. So we get these ellipses, and they are not so if we assume for now that U equals U prime, which is the most common case in zero-sum games, for example, then where before we had perfect circles, now we have essentially ellipses that are rotating around it. And we also know that each player knows their Nash equilibrium. So now comes one idea. Okay, what happens if a particular player, say player A, is moving away from their Nash equilibrium? We show now that if he is indeed moving away, then he's also winning. Winning means that their current vector payout compared to their reference payout, which is the Nash equilibrium, is larger than zero, right? Otherwise, they would be losing. And if you plug in the conditions, you can factor it out into this number, that the product of alpha minus alpha star, so the difference to your equilibrium probability times essentially your gradient of your payout function, or expected payout for your strategy parameter. And of course, if this is guaranteed to be larger than zero, there are two cases. Either you are on the right-hand side of your equilibrium point, so alpha minus alpha star is larger than zero, but that also then implies that your gradient with respect to the alpha parameter is also positive. And a positive gradient means that your alpha is growing, so you are already on the right of your equilibrium parameter, and now you're moving even further away from it. And the same is of course true for the case where alpha minus alpha star is negative. You're to the left of your equilibrium point, yet your algorithm pushes you even further to the left. And exactly the same is true for the column player. If the column player, you just replace alpha by beta, but everything else is exactly the same.
Sorry, you were saying right and left there. But I've lost track there.
So it's probably easiest if you look at it in the quadrants. So if this red line is the center of player 1. That means where he is on the alpha value that corresponds to the alpha value of his equilibrium. Right. So now what we're saying is that when we are somewhere here, say it's in the first quadrant, the alpha value here is larger than the alpha value at the center. And we have just proven that if he follows Wolf-Igger, then the gradient of Wolf is pointing towards the right from the point of view of player 1. So he's the moment he wins, he is moving to the right. If he is on the if his alpha is larger than the central point, so he's actually moving away from the equilibrium. The same way down here in quadrant 3, he is winning, but his alpha is now here smaller than his center value, and he's still moving to the left. And the same is true for player 2. If player 2 is winning up here, then he's moving away from his center, which is the red line. But in this case, player 1, because player 1 is losing, he's moving closer to his center. Do you see?
Yeah, that makes much more sense. I was confused about the flip over when the
Yeah,
player starts to lose. That's the bit that was missing out there. Yeah,
the important bit is that in each quadrant, a player is either winning or losing, and the only time where it changes is actually when we cross the center. When we cross the center, we go from, say, in quadrant A, player wins and player 2 loses, to the situation where player 1 loses and player 2 wins, and then so on and so forth. And of course, if in standard Igger, these circles are essentially indefinite, and so you always go from times where one player wins and the other one loses to the ones where it's the opposite, and then it flips back and forth, and then you essentially go round and round. Now, what happens now in Wolf-Igger is that if we lose, actually what we do is we cut down our learning rate, whereas the loser is actually speeding up the learning rate. What that means is that one player is moving away from their stable position, but slows down, whereas the other one who is going towards their stable position is moving faster. And so if you and in each case it's essentially an ellipsis we have the equations for. So we start at some deviation from the equilibrium, and if we ignore Wolf-Igger, we just keep their L values as constant, we get an ellipsis, and the ellipsis is elongated towards the side that is currently losing. So we fall back faster to the losing edge than to the winning one. But the moment we hit the center for one of the players, the behavior changes. We're still on an ellipsis, but now the ellipsis is actually elongated in the other direction. And so rather than following the original ellipsis, we actually now on a different ellipsis path that ends up closer to the center as we started out with. And we can actually do the full circle, and every time our strategy behavior changes, so one player goes from winning to losing, we essentially acquire a prefactor, so that once we have been going once around, we actually are multiplying our original deviation, beta naught, with L min over L max square. So and we always said that our minimum Wolf factor is smaller than our maximum Wolf factor, right? We slow down as we're winning rather than speeding up. In that moment, what started out with as a stable ellipsis is essentially imploding on itself and moving closer and closer to the center of the equilibrium. Does it make sense?
That makes sense to me. That's really nice.
Cool. And it is not even the case. You don't even have to demand that the one player slows down as much as the other player is speeding up. As long as this ratio is fulfilled, that the product of one player slowing down to speeding up is the same. The product of these slowing down factors is smaller than 1. You're always going to end up in the situation where you're spiraling closer and closer to the center. If you would turn it around, then of course you would spiral outwards and the whole thing becomes unstable again. How does it look in practice? Because the one of the negative things was you actually have to know what your stable reference solutions are, right? Even though we know that in say zero-sum games there is definitely a net equilibrium and we can calculate it, it still kind of sucks that we have to do that. And in this practical algorithm, they start out with policy hill climbing. It's rational, but it's not convergent. But it has some nice property, namely that the policy that you learn is not a pure strategy anymore, but rather policy hill climbing already allows you to come up with mixed strategies. Let's actually have a look. So what you do is, it's your standard queue updating. However, you also keep as a sidetrack your policy, and where before your policy would have been just whatever is the action that is currently the maximum of your queue function. Now you keep a memory of your action. You just update a little bit by nudging it in the direction that is slightly better, that is maximizing your queue function. So if your queue function, for example, say in rock, paper, scissors, switches a lot between all 3 states being currently the best, because you never update completely, you essentially are much more incentivized to be close to your central policy. It's tunable, right? So if you make this delta update larger and larger, eventually you become greedy again, that whatever action happens to be the best becomes the full weight. But if you make a delta smaller, it's only nudges you in the right direction, and equally, of course, takes weight away from the other direction. And they took this policy hill climbing and they extended it to make it more wolf. Essentially, what you do is, as a reference policy, rather than calculating the net equilibrium itself, you keep track of, in your past, you know the probability distribution of actions you would have chosen, so you can give each action essentially the weight it would have been given over the last number of plays whenever you were in that particular state, and calculate an average policy you would assign to that action. And so it's just a very fancy way of updating that. Otherwise, it's still the same, that you nudge your policy only ever so slightly, so you never go greedy all in. But now the way you nudge is by nudging slightly less even when you are winning compared to your reference distribution, the reference distribution being just the average policy that you would have been played if you have been playing it all along, or make it a bit larger when you're winning. And so that is the wolf part, essentially. And they put it in place. They tried different values, so the ratio between winning delta and losing delta. Of course, we always want to speed up when we're losing. How much we speed up, that is a hyperparameter. And they said on matrix games, so they don't traverse like a deep state level system, you can get away with smaller values. And for stochastic games, so we have more than one state, you have larger values. And they also implemented it so that your updates become smaller, so the value updates and everything become smaller the more often you've been in a state. So if you have a starting state that you visit very often, eventually you're going to learn less and less about it. But that is a detail that is not really necessary. And apart from that, it's a fairly stable algorithm. So here, that is the penny matching, where we know that the stable policy is 50-50, and the policy hill climbing, so the one that doesn't use this win or learn fast, is one that is bouncing around in these large circles. whereas the wolf policy hill climbing converges rather quickly to a fairly stable solution and just moves very small steps around it. The same they did for rock, paper, scissors. And they found it works really quite well also on stochastic games. On games where you have higher dimensions, so more actions, more states and everything, you have to do more fine-tuning in order to find parameters of these wolf acceleration or deceleration to make it stable. But generally, it seems to be converging better in wolf than without using wolf. And I tried it as well for my rock, paper, scissors on the imbalanced rock, paper, scissors, and you see that actually very quickly you start in the middle, but the policies that are being trained are actually hovering around the correct equilibrium points that are calculated using a Nash solver. So started out somewhere here and very quickly ended up around the point. Now, if I make delta actually smaller, so my update's even smaller, it becomes also a lot smoother. Then essentially the variance around the equilibrium point becomes less and less and less, and it smooths out. And yeah, you will see that the red cloud essentially moves closer to the true value. But interesting enough, the average policy, because we average over smaller and smaller space, the average policy actually relatively quickly converges really well to the Nash equilibrium. So without explicitly knowing about the Nash equilibrium, and so that seems to be, at least for the small matrix game I tried it against, very stable, and yeah, just works and made me very happy. So there's a summary that a gradient solution in the state space stochastic games, where you vary your learning rates based on whether you're winning or losing, can help in stabilizing your algorithms and finding Nash equilibria. And it has been proven for a two-player, two-action game mathematically. It has been actually also shown in larger games where we haven't proven it mathematically, but empirically it seems to work still really well. You don't actually need to explicitly calculate the Nash equilibrium, just by taking the averaging and letting it getting close enough that it can find it. It will eventually reach it by itself. Depends on the game, of course. If there are more Nash equilibria, then it might still you might still have to sample different starting positions in order to see where you're going to end up with your equilibria. There are still some parametric dependencies that are hard to reason about, especially once your game gets bigger and noisier. Yeah, like calculating stuff on the average policy generally made things a lot smoother. And of course, as the state space gets really large, it becomes very memory inefficient. And at that point, you probably want to have a model that, rather than counting the states, you have a model that sort of abstracts from the state space itself what is how similar states are. Think of poker. Right? Poker, you have a very large number of possible hands, but some hands are more similar than others. So finding a model that works on that is hard, but numerically at some point necessary. The problem is, in a lot of these cases, the convergence is less guaranteed, and there are in fact some how do you call it, instabilities. I'm probably not going to do eventually a paper about that. Is actually really quite interesting. I do think that this zero-sum Wolf-Igor can be probably extended to larger dimensions than just two-player, two actions, because it somehow feels intuitive that because always one player is winning versus the other one is losing, as long as the winning one is moving slower than the faster one, you're probably always going to move closer in sum total towards that state. And I think something like deep wolf should be possible, but so far I haven't gotten it to work really. And there's another very interesting paper that is quite a lot later than that. It is a paper where they use deep learning or deep reinforcement learning, but they specifically have the opponent's strategy as a policy in their system, and the algorithm sort of checks out first, okay, we both see the same game. If I was the opponent, how would I update my policy? And they use that then as an input into their loss to sort of use the anticipated learning of the opponent to optimize their own policy improvement, and that supposedly also converges to Nash equilibrium, something I want to try next. Yeah, that would be it.
Cool. Thank you so much, Arvid. Any more questions or comments before we wrap up? I'll stop the recording.
Yeah, sorry, overrun quite a bit.
Yeah, no worries. How I don't know how to stop the recording. Okay, cool.